Mr. Corsi here. In this video we're going to look at dividing two complex numbers, in particular what the resulting modulus is and what the resulting principal value of the argument is. So let's have a look first at this complex number z1, and here's its argument shown. And it has a polar form of 2 cos 1 plus I sine 1. So this angle is 1 radian and the modulus is 2. Now let's have a look at z2, which is precisely the same, and ask ourselves the question, suppose we divide these two complex numbers, z1 divided by z2, where they're both equal. Now normally 3 divided by 3, 8 divided by 8, you'd get 1. Let's see if that's true. Well, it is. So what can we say about what's happened to the two moduli? Well, it would appear possibly that 2 divided by 2 gives you 1. And what's happened to the two arguments? Well, possibly 1 minus 1 gives you 0. So possibly the pattern is that we divide the two moduli to get the resulting moduli, and that we subtract the two arguments to get the resulting argument. So let's now change z2 so that it becomes the number 1. And there's another one we should know, that if z1 divided by 1 should give us z1. Let's check. And there it is, z1 divided by z2 is exactly the same as z1. And again, let's check. The modulus of z1 divided by the modulus of z2 does give us the modulus of z1 divided by z2. And 1 minus 0 for the arguments gives you 1. Now let's try and increase the argument of z2. And let's check what's going on here for the arguments. We'll not look at the moduli, let's just look at the arguments. 1, subtract 0.28 and we'll get 0.72. So as we increase the argument of z2, the argument of z1 over z2 decreases by the same amount. There's 1 minus 0.7 gives us 0.3. And when the two arguments become identical, and we subtract them, we'll get a complex number on the real axis, a real number in effect. So we subtract these two arguments to get the argument of z1 over z2. And that continues as the argument of z2 is greater now than the argument of z1. You can see the argument of z1 divided by z2 has gone negative. 1 minus 1.16 gives you negative 0.16. And the resulting complex number z1 over z2 has now appeared in the fourth quadrant. And there's one where we can look at the 2 divided by 3 for the moduli. We get approximately 0.67 if it's rounded. 1 minus 0 gives you 1. So in all cases, we see the pattern that the modulus of z1 over z2 is the modulus of z1 over the modulus of z2, which is a result we know already from previous videos, and that the argument of z1 over z2 is the argument of z1 minus the argument of z2. So let's attempt now to prove these results mathematically. So let's start with two complex numbers, z1 equals r1 cos theta 1 plus I sin theta 1, and z2, which is r2 cos theta 2 plus I sin theta 2. And we're going to divide z1 by z2. So that's r1 cos theta 1 plus I sin theta 1 divided by r2 cos theta 2 plus I sin theta 2. And we'll use the usual trick of multiplying top and bottom by the complex conjugate of the, in this case, of z2. So cos theta 2 minus I sin theta 2 over cos theta 2 minus I sin theta 2, or in effect multiplying by 1. So on the top we've got a real part which consists of multiplying the first two terms together. That's cos theta 1 cos theta 2. And the last two terms, which would be negative I squared, which is plus 1 sin theta 1 sin theta 2. And then the imaginary term comes from the inside 2, sin theta 1 cos theta 2, and the last two terms, which is minus cos theta 1 sin theta 2. And then the denominator, that'll be r2, and then our first two terms give us cos theta 2 squared, and the inside outside 2 cancel. Last give us minus I squared, which is plus 1 sin theta 2 sin theta 2, so sin squared theta 2. And we know that's 1 on the bottom line, r2 times 1. So the top line, you'll notice that if we expand cosine theta 1 minus theta 2, we get cos cos plus sin sin. That's the expansion, the addition formula for cosine. And similarly, if we expand sin theta 1 minus theta 2, we get a sin cos cos sin, with the minus staying as minus. So we've ended up with a one complex number, and its modulus, so the modulus of z1 over z2 is r1 over r2, which is the modulus of z1 divided by the modulus of z2. Now that's a formula we knew anyway. And also, let's talk about principal values of the argument. So let's decide on the principal value of z1 over z2. Let's assume these were also principal values. We'll have a principal value of z1, which is arg z1 minus principal value of z2, which is arg z2. Now, as we saw when we were multiplying these, we sometimes have to adjust by adding 2 pi, or not adjust, or subtract 2 pi. So we have to add a multiple of 2 pi, n times 2 pi, where n is either negative 1, 1, 0 or 1. Now that adjustment is made because occasionally when we subtract these two arguments, it'll be out with the principal argument range. So that really is the best we can do for the argument, and there is the result. So a very familiar result for the modulus, and a maybe not so familiar result for the arguments, but division of the moduli and a subtraction of the arguments. So after that, let's see if we can tackle an example. So in actual fact, we've got 3 examples here. So if you could maybe stop the video and attempt these, and then we'll tackle them. So let's tackle question 1. And to do this, we're going to get I and negative I in their polar forms. So let's look at a diagram and see where exactly these complex numbers are. So there's I, and we can see that its principal value of the argument is pi upon 2. And there's negative I, and its principal value we can see is negative pi upon 2. Now both of these complex numbers have unit modulus. Modulus is 1. So I we can write as 1 times cos pi upon 2 plus I sin pi upon 2. And negative I we can write as 1 times cos negative pi upon 2 plus I sin negative pi upon 2. And the result of dividing complex numbers in polar forms means that we divide the moduli. 1 divided by 1 is 1, and we subtract the argument. So pi upon 2 minus negative pi upon 2 is pi upon 2 plus pi upon 2, which is pi. And now we just have to evaluate cosine of pi. Remember, the cosine of pi is -1. And the sine of pi is 0. So we've got 1 times -1, which gives us -1. So that's us finished example 1. And let's now move on to example 2. So in this question we're looking at 1 divided by 1 minus I. And using polar forms again, let's have a look at a diagram of this and find where these numbers are. So there's the number 1. It obviously has a modulus of 1 and a principal value of the argument is 0. So that's 1 times cos 0 plus I sin 0. And let's look for 1 minus I. Well, it's down there. And its argument would be negative pi upon 4. Imagine a unit square there. And therefore its argument, its modulus is root 2. So there's its polar form. And again, remember, dividing two complex numbers in polar form, we divide the moduli, so that would be 1 over root 2, and we subtract the argument. So 0 minus negative pi upon 4 is pi upon 4. So we end up with trying to evaluate cos pi upon 4, that's 1 upon root 2, and sin pi upon 4 is 1 upon root 2 also. And let's multiply out. 1 upon root 2 times 1 upon root 2 is 1/2. And similarly here. So it's 1/2 plus 1/2 I. So there's our answer to question 2. Now, incidentally, there is another, probably more convenient way of working this out, where we multiply top and bottom by the complex conjugate of the denominator, which in this case would be 1 plus I. And so on the top of this fraction we get 1 plus I. The firsts would give us 1. Insides and outsides cancel, and our last give us negative I squared, which is plus 1. So we get 1 plus I over 2. And splitting that into its two constituent parts, we get 1/2 plus 1/2 I as we had before. And it's nice to see that tying up with what we got using polar form. So finally, let's tackle example 3. Now, before we launch into this question, it's useful to remind ourselves that when we're looking at complex numbers with a root 3 in them, that we should be searching for this diagram, which is an equilateral triangle of side 2 chopped in half, and we get a 1, 2, root 3 right-angled triangle where the two angles are pi upon 3 and pi upon 6. So let's look at part A. We're asked first of all to find the polar form of two complex numbers. First one is -1 plus root 3i. And let's try and locate that on the Argand diagram. So 1 to the left and root 3 up. And we're trying to find that equilateral triangle that we talked about. That's length 1, that's root 3, and that's 2. So there is the equilateral triangle. So this angle in particular is pi upon 3. So the rest of this angle is 2 pi upon 3. So that gives us the principal argument of -1 plus root 3i, and it gives us the modulus of it. So we can write it now in polar form. It's 2 times cos 2 pi upon 3 plus I sine 2 pi upon 3. And the second complex number that we're trying to find the polar coordinate for, the polar form for, is -root 3 minus I. And let's try and locate that. So -root 3 minus I. So again, if we make up that right angle triangle, that side is root 3, that's 1, so that'll be 2, and we can see where that equilateral triangle is. And therefore this angle in here is now pi upon 6. The remainder of that angle round to the real axis there is 5 pi upon 6. So the principal value of that complex number is -5 pi upon 6 with modulus 2. So that's part A. We've found the polar forms. Let's move on now to part B. We're asked to use these polar forms to evaluate Z1 divided by Z2. So remember, the modulus will be the two moduli divided. 2 divided by 2 is 1. And the arguments are subtracted. So we will have 2 pi upon 3 minus -5 pi upon 3, which is 5 pi upon 6. So there's a little calculation that we'll have to do. 2 pi upon 3 plus 5 pi upon 6. Let's think in terms of pi upon 6's, so double top and bottom here, 4 pi upon 6 plus 5 lots of pi upon 6. That'll be 9 lots of pi upon 6. Now you'll notice that's greater than pi. 6 lots of pi upon 6 is pi. So if we take away 2 pi from that, which is 12 lots of pi upon 6, we'll end up with -3 pi upon 6 for the principal value of the argument, and that's -pi pi upon 2. So let's use that. And now we'll need to evaluate cosine of negative pi upon 2. Let's look at the cosine graph. Starts at 1, goes in negative 1 back up to 1 again. Negative pi upon 2 will be 0. And similar investigation of the sine graph, goes up to 1, negative 1 back up to 0, but negative pi upon 2 will be negative 1 for that value. So we end up with negative I as our evaluation of Z1 over Z2. Now we're asked in part C to find an alternative way of doing this without going through the polar form. So let's look at this division. It's negative 1 plus root 3I over negative 3 minus I. And the only way of moving forward with this is to multiply top and bottom by the complex conjugate of the denominator. So the conjugate of the denominator is negative root 3 plus I. So we'd be attempting to multiply top and bottom by that complex number. So let's see how that goes. So the real part of this product will come from the firsts, which is negative 1 times negative root 3, and the lasts. Now that's positive root 3i squared, which is negative root 3. So there's the real part. And the imaginary part will come from the insides and the outsides. So the inside two give us negative root 3 times root 3, that's negative 3i plus negative 1i. So that's negative 3, and that's minus 1. And the real part comes from negative root 3 times negative root 3, which is positive 3, and also negative I times I, which is negative I squared, which is plus 1. Then the imaginary part comes from the insides and the outsides. Inside 2 give us positive root 3, and the outside terms give us negative root 3i. So that needs tidied up. The real part in the top line is 0, and the imaginary part is negative 4. So we get negative 4i on the top of the fraction. Real part on the bottom is 4, and the imaginary part is 0, so that's 0i. So negative 4 divided by 4 is negative 1, negative 1i, which is what we had before. So there's another method of producing the negative I that does not rely on changing the two fractions into polar form. So that's Mr. Corsi signing out, and hope you enjoyed the video.